Okay, so let's talk about the last couple points of inverse relations and functions. On your note sheet from the first part of this section, we talked about two things. The first property was the domain and range should switch for a function and its inverse. And then the second thing was that a function and its inverse graphically, they should be reflections of each other over the line y equals x. So the last two things we're going to look at is point number 3. Well, let's think back, way back to the first semester. If the graph of an equation passes the vertical line test, then it should be a function, meaning each input has one output. Point number 3 then, so on your note sheet, if you want to fill out property number 3 for a function and its inverse, is if a function passes the horizontal line test, then the inverse should also be a function. So if the original passes the horizontal line test, then the inverse has to be a function. So let's look down at just your basic parabola, y equals x squared. Notice that this passes the vertical line test, meaning a vertical line will intersect the graph in most at one spot. So each input has one output. But if I draw a horizontal line that intersects the graph at more than one point, then this fails the horizontal line test, which means the inverse will not be a function. Now, instead of memorizing this, if you remember that in order to graph the inverse would be y equals plus or minus the square root of x. One thing was I could reflect this over the line y equals x. So here's my line y equals x. Sort of, should go through the origin there. If I reflect over the line y equals x, I actually end up getting, okay, there we go. If I reflect over the line y equals x, this is my inverse function. And if you notice, okay, well, where does this horizontal line go when I reflect the original parabola to get the inverse? Well, that horizontal line would become a vertical line if I reflect. So if the original fails the horizontal line test, that means the inverse is going to fail the vertical line test. Therefore, the inverse is not going to be a function. So let's take a look at y equals x cubed, your basic cubic graph. This should pass the vertical line test. At most, any vertical line intersects the graph and in most one point. So each input has one output. And then if I draw horizontal lines in a similar manner, any horizontal line also will cross the graph in at most one point. So since this graph passes the horizontal line test, that actually means that the inverse will be a function. And we can look at sketching the inverse here. So if I sketch, the inverse would be what? Y equals the cube root of x. If we sketch that graph, it would look something like this. And this horizontal line, if I reflect over the line y equals x to get the inverse, that would now become a vertical line. So this should pass, the inverse is going to pass the vertical line test because the original function passed the horizontal line test. So let's see what you gathered from that. Why don't you pause the video at this time to determine which of these functions have inverses that are also functions. So pause the video. First thing to note is all of these original graphs are functions. They all pass the vertical line test, but only two of them pass the horizontal line test. So the bottom left, this one passes the horizontal line test. Any horizontal line touches the graph at most one spot. Second, this also passes the horizontal line test, which means the inverse of these graphs would be functions. because the inverse would pass the vertical line test. Here, let's look at the others. I mean, here you can see, yep, this horizontal line crosses the graph in more than one spot, so that fails the horizontal line test. This fails the horizontal line test. That's your absolute value function. The parabola fails the horizontal line test. And certainly, a horizontal line is going to fail the horizontal line test. So if the horizontal line crosses the graph at more than one spot, that means that the inverse will not be a function. So the original might be a function if it passes the vertical line test, but the inverse isn't a function because the original graph fails the horizontal line test. So with that being said, there's one more property that we really need to look at for inverse functions. We talked about this the other day, inverse operations. Note that, if I start at 10 and I add 5 and then I subtract 5, addition and subtraction undo each other. I'm back where I started. Multiplication and division, those would undo each other. If I take the square root of 49 and then square it, I'd be right back at 49. And the same can be said for cubing. If I cube 2 and then take the cube root, I'm right back where I started. The inverse operations, they undo each other. So inverse functions also undo each other. Let's look at the homework from last night. Here's one of your homework answers, so you can actually check to see if you got that right. That should be your inverse equation. Let's say I want to find f of f inverse of 7. So I'd want to start at the innermost parentheses, and let's find f inverse of 7, meaning I want to take my inverse function and plug in 7 anywhere I see x. So I'd have 1 times 7, or 7 over 9, plus 2 over 9. Add your fractions, so add your numerators would give you 9 over 9, and that would just be 1. So if I want to find f of f inverse of 7, so this is what I'm asking you to do. Well, I just found that f inverse of 7, that this was actually 1. So really what I'm asking you to do is take f of 1, since f inverse of 7 is 1. So now look to my original function, plug in 9 anywhere I see x. So plug in 1, anywhere I see x. So 9 times 1 minus 2 should give you 7. Did you catch what happened here? So I plugged 7 into the inverse function, and then what came out, I plugged that into the original, and I should end up with 7. These functions actually undo each other, and I'm right back where I started. Let's check the other way. What if I want to do f inverse of f of 7? Okay, so let's start with f of 7. I input 7 into function f. 63 minus 2 is 61. So really what I'm asking you to do, f inverse of f of 7, well, that would be the same as saying, well, f of 7 is actually 61. So I want to input 61 into my inverse function. So 61 over 9 plus 2 over 9, I'd get 63 over 9. Which is 7. Now maybe you're catching on here and thinking, oh yeah, there's a shortcut. So I plug 7 into the original, what comes out goes into the inverse. Do I need to do all this work? Because I should end up with 7. Inverse functions undo each other. You could check number 4 from the homework. So this should have been your answer from last night. You can go ahead and check. If I ask you to find h of h inverse of 32, well, these are inverse functions. However, whatever h inverse does to the function, h should undo it, and I should be right back where I started at 32. So I can kind of cut all this middle work out. And if I do the reverse, if I plug 32 into my original, and then whatever comes out, I plug it into the inverse, okay, I do all this work, well, these functions just undo each other, and I'm right back where I started with 32. So now I don't really have to do all of this work in between. If I know what the inverse function means, it means I should be right back where I started. That brings us to the last property then of inverse functions. So the definition of inverse functions. Functions f and g are inverses of each other if and only if f of g of x equals x and g of f of x equals x. So one thing to note is that if I find the inverse of a function, the inverse doesn't have to be a function. But if I have two functions that are inverses, then if I plug one into the other, if I plug x into g and then g into f, and these are inverses, I should be right back where I started. Just like on the previous page when I plugged in 32 into a function and then its inverse, I was right back at 32. And then the reverse should be true also. So if I start by plugging x into function f, and then whatever comes out, I plug that into g, and if these are inverses, I should be right back where I started with x. So if I want to prove functions are inverses, these are the two things that I need to show. Make sure you need to show both of them. Showing just one of these isn't sufficient to prove that these are actually inverses. And I also don't want to just plug in a number. That would mean that it only works for a specific case. So I want to keep my proof in general and show that if I plug in x to a function and its inverse, I get out x, where x can be any number. So if I'm asking you to prove functions are inverses, we need to use the definition. This is from the notes from yesterday. We came up with the inverse function. So let's actually show that these are inverses. So going back to the previous page, this is what I need. This is my goal right down here. I want to show that if I start with the inverse, plug x into the inverse, whatever comes out, I plug it into the original, I'm back where I started. And the reverse, if I first plug into the original, whatever comes out, I plug it into the inverse, they undo each other, and I'm right back where I started. So step one, let's start by showing f of the inverse of f of x. I want to show that eventually, if I go through all the algebra, I should end up right back where I started with x. Now make sure you're actually showing the work step by step. Okay, so I'm taking f of, well, the inverse function. This is actually just 7x minus 2, the quantity to the 1/5 power. So I want to take this function and I'm plugging it in anywhere I see x. So f of, well, the inverse is this. So I'm taking this and I'm plugging it into the original function, which would give me, okay, so here it is, I'm plugging this in, 7x minus 2 to the 1/5, plugging that into function f. So anywhere I see an x, I'm replacing it with 7x minus 2, the quantity to the 1/5 power. So I'm raising that to the 5th, I'm adding 2, and I'm dividing by 7. So there's my composite function. I'm plugging the inverse into the original. Now all I have to do from here is kind of clean this up line by line. So don't skip a bunch of steps at once. If this is a proof, you should be doing kind of one thing for every step. So next you can notice, well, okay, the 5th power and the 5th root, those would cancel each other out. So I would have 7x minus 2 plus 2 over 7. Well, negative 2 plus 2, that would just be 0. So I have 7x over 7. And then last step, 7 divided by 7 leaves me with x. And this is what I wanted to show, that whatever I plug in, the functions undo each other. That's what I get out. Okay, now again, we're not quite done yet. I need to do the reverse. So now let's look at if I start with the original function and plug that into the inverse, I should also get out x. So step 2, taking the original, here it is. Again, this is a good review of composite functions. So I'm taking that and I'm plugging it into the inverse anywhere I see x. So f of x is actually all of this stuff. This is what I'm inputting. Whoops. This is what I'm inputting. Okay, let's try that again. 2, right? Oh, struggling here. There we go. That's what I'm inputting into the inverse function. So if I actually do that, I'm going to get 7 times. Okay, here's what I'm inputting. I'm going to replace x with x to the 5th plus 2 over 7 minus 2. All of that to the 1/5 power. So here's my next line now. I just canceled out, if I'm multiplying by 7, dividing by 7, those will go away. And step by step, if I'm adding 2, subtracting 2, then I'd have x to the 5th to the 1/5. And I have an exponent to an exponent. 5 times a 5th would just give me x to the 1st power. And this is what I wanted to show, that if I plugged in x to my original function, then to the inverse, they undo each other, and I'm right back where I started. So therefore, by showing these two things, you need both of them, I have showed that these are indeed inverse functions. All right, proofs, gotta love them.